grad student area, or not office period is and then the fourth floor. Yeah, so I tried.
Oh wait, in the
maintenance.
When is your DOC plan?
not for a while. I know, I'm sorry. It's been like, no, not doing great things. I miss you guys so much. You have no idea.
No one says that. Yeah.
Except for me.
Started this question. I just didn't even try it.
Right.
Sorry,
I missed yours.
You also
What are the bad? I came back. Did come thank you very much.
hoping I speak up.
Contractually obligated. Okay. Because I have samples now. I'm not gonna lie. I run and change columns. I got like halfway through it so that you have a nice column for next week. I got a really long time to go.
Okay, you can flip on it. My experiment is in progress, so it's
Okay. Yeah. This one thing, like, are you doing the one where you're adding a specific amount of DNC, adding like?
yeah, and so right now they're drawing on 20 micromolar, which is like 0.25 ppm. And I don't want to analyze that, so I was going to add in pH to bring it up to. Yeah, so I was a bit nervous about the technical variability.
Is it on the final?
It's your experiment, go for it.
What do you guys think?
I don't know. I don't think it's the bugs. I think it's the bugs. I think there's something else. But I think this is going to confirm that.
Every time we're like, this is the one.
No,
this is the one
saying.
that is going to tell me everything you know. All I'm really looking for is the perfect match. The perfect
You sound like
game
you're
plan.
Sound like you're an
Get data.
perfect data.
Yeah. I'm not trying to just true. Yeah.
There isn't tonight.
That's a mess. I'm like, where's that coast?
Yeah, exactly.
I hope so.
I haven't heard.
I wouldn't know.
Oh my god.
Like
I would be surprised. The first gypsy. Yeah. Usually it's like every other Monday, but it's like
every Monday and a Friday.
Yeah.
Okay, thanks everybody for coming. It's a pleasure to introduce Nathan McTigue from NOAA is our speaker today. A little bit of background: Nathan did his undergraduate work at the University of Georgia, and got his PhD at the University of Texas, part of the South, two of the three coasts, and he is now an NRC, National Research Council, postdoctoral fellow at NOAA at the coast in Beaufort. And so Nathan's going to tell us about been doing in the last 2 or 3 years on carbon sequestration.
Great. Thanks, Brent, for the introduction. Thank you all for your attendance and attention. Thanks for lunch. Treating me. Nice. Thank you to Matt Kenworthy for showing up late. Yes, as Brent said, I'm going to walk you through some work I've been doing over the past few years at NOAA on the North Carolina coast. And sort of looking at this large scale, ecosystem scale biogeochemistry problem. And relating it to what so often is related to environmental sciences, this problem of climate change. But since I have a captive audience, I'm going to take the liberty of taking a very tangential approach before I finally get to the problem. And approaches from a long way off. And to me, it's just interesting to go back and look at historical science. And we're going to go back to 1896 when Svante Arrhenius, he's got regions named after him, he's done a lot for the world of chemistry. He wrote this paper, letter, on the influence of carbonic acid in the air on the temperature of the ground. And so Arrhenius and his peers at the time were really interested in why the temperature of Earth is different than the temperature of the moon. And they figured it had something to do with the atmosphere and the greenhouse gases that our atmosphere has. They identified water vapor as a greenhouse gas and carbonic acid, CO2, even though it's a trace gas, as this important factor in regulating climate. And Arrhenius goes on to say, maybe the concentration of greenhouse gases in the atmosphere is responsible for the beginning, the initiations, and the endings of ice ages. And so it's cited as one of the first times greenhouse gases is sort of brought to the limelight. Interestingly, towards the end of the paper, he talks about sources of CO2, and he brings about fossil fuel combustion as a source of CO2. And there's a back of the envelope calculation of coal combustion at the time, and back of the envelope calculation for limestone formation. It says they compensate each other. The fossil fuel combustion isn't that significant. And I don't know much about limestone formation, so I can't check his calculation, but I will say his coal combustion, although probably accurate for the time, doesn't foresee the industrialization of the world, and gasoline internal combustion engine was an invention in its infancy at the time. So it's just interesting to see how the great minds of the past sort of saw problems and how we continually take these same problems and evolve them. So fast forward several decades, and we have one of the most famous graphs in environmental science, maybe all of science, the Keeling curve, which was started to try to measure this trace gas in the atmosphere. It's only 0.03% at the time. It's a very minuscule component of the atmosphere to measure it. And one of Keeling's first observations was a seasonal cycle that no one knew about. And so now, as a modern scientist out here, we're dealing with this problem of how does global climate change affect our ecosystems that we study. To me, what's interesting is flipping that around a little bit and thinking, how do our ecosystems that we study affect climate change? And can there be feedbacks? Are there positive feedbacks where climate change causes our ecosystems to produce more CO2? Or the opposite, where possibly our ecosystems can take away some of that CO2 in the atmosphere that's causing this problem? And so this idea of geoengineering involves changing Earth's climate and regulating it and undoing some of these deleterious effects climate change is causing. And divisions of chemistry and physics are frantically trying to find that billion-dollar patent to sequester carbon dioxide from the atmosphere, store it away for long periods of time, therefore possibly regulating climate change. But the caveat is that it cannot create more CO2 than it captures. So for a society that revolves around fossil fuels and internal combustion engines, that's oftentimes difficult. But in the end, this geoengineering solution looks something like a carbon dioxide vacuum. Well, I want to point your mind to another technology that exists. It's 2 billion years old. It's solar powered, and photosynthesis all around us sequesters CO2 from the atmosphere and turns it into organic carbon, stored away as non-CO2. Most of that CO2 is converted into sugars, and the plants use it to survive, so it's returned right back into the atmosphere, but portions of it are stored as biomass or other compounds that get buried away. This is a really interesting idea that we don't need to invent something to do this. It's already happening all around us. And possibly the natural ecosystems can be used as a geoengineering tool. So this isn't entirely a new idea. I'll go back a couple of decades to the iron hypothesis. So John Martin, a nutrient chemist, hypothesized that the HNLC, the high nutrient, low chlorophyll zones, were limited by micronutrients like iron. And given that micronutrient caused gigantic phytoplankton bloom, which would suck up CO2 from the atmosphere, sink to the bottom of the ocean, removing that CO2 from the atmosphere. And eventually this hypothesis was tested on a larger scale. It didn't create an ice age. It did temporarily remove CO2 from the atmosphere. Problem with phytoplankton is it remineralizes, it decomposes very quickly, and it didn't all sink away really fast. And on the larger scale, thinking about taking one step back, looking at a bigger picture, the tanker carrying tons of iron is going to be burning lots of diesel, and the mining process of iron takes a lot of carbon dioxide. So it's not really a true solution, but this sort of idea, it intrigued a lot of people, and that creativity might hold one of the solutions to solving this geoengineering problem. So a few years after John Martin and the Iron X experiments, the UN came out with 2 documents. One, the natural fix, the role of ecosystems in climate mitigation. And this document outlines all of the terrestrial ecosystems of the world and how much carbon that those ecosystems store and how much carbon they can take up through photosynthesis. The title is very misleading, but it's really catchy. The natural fix. How can these things that already exist that I don't need to change my behavior, how can they help mitigate climate change? And spurring off of this was one of the first blue carbon documents that actually defined this idea and coined this term, blue carbon. So what is blue carbon? I'm going to answer my own question with a non-answer first and try to relate it to an analog you may be familiar with. It's the RED, or the Red program. And what RED did was take the standing biomass of terrestrial forest and all the carbon that's stored there and somehow monetize it and make it worth something, so that developing countries have a reason to not send people out to slash and burn the rainforest, farm corn for a year, and then abandon it because it can't yield crops go burn the next acre of rainforest. So monetizing this carbon stock actually preserves that forest and gives some value to the ecosystem. So blue carbon started as this same sort of idea in that salt marshes, mangroves, and even seagrasses possess large stores of carbon that when they're disturbed or maybe starting a shrimp farm, might release that carbon and change the ecosystem function for the worst. And so giving those ecosystems value and this catchy term would help preserve the ecosystem. But as an offshoot from this initial idea, were these ideas of blue carbon sinks and blue carbon production, and that these coastal vegetated ecosystems draw down carbon and have value in their potential for geoengineering. So this sounds kind of crazy when you think about the the extremely small area of wetlands. Wetlands they're like a layer of paint around the continent, right, compared to the actual area of the rest of the vegetated ecosystem. And mangrove, seagrasses, and salt marshes together are less than 2% of the rest of the area of just forest area. It doesn't include peatlands and grasslands. So how could this very small area be so important in the carbon cycle? Well, it has to do with the carbon burial rate, or as I'll refer to, the carbon accumulation rate for the rest of this talk. And in this graph on the y-axis, McLeod et al. Shows this carbon accumulation rate. And the y-axis is the log scale. And the first 3 bars are forest ecosystems, and the next 3 is salt marsh, mangrove, and seagrasses. And you can see, remembering that we're in a log scale, that these ecosystems have at least 10-fold more potential to draw down and so-called bury carbon. And by doing the math here, our units of carbon accumulation rate, grams of carbon per square meter per year, multiply that by our area. And as a global whole, wetlands, even though they're just a fractional of the area, can potentially bury just as much carbon. And so by making a concerted effort on a very small amount of area, you get a lot of bang for your buck. However, this whole idea hinges on what the carbon accumulation is. This paper pulls together, the literature review pulled together a lot of different sources and found this mean rate of 244 grams of carbon per square meter per year to represent the world's wetlands. But this error bar is gigantic. So it's a log scale error bar. And the actual rates range from 3 to 1,700 grams of carbon per square meter per year. That astronomical range. And so depending on where that true rate really falls, means a lot for whether this bang for your buck really holds true. So from that important seminal blue carbon paper, they got a lot of people thinking about what is this blue carbon production? How much do wetlands really draw down carbon? A lot of blue carbon papers have been the product of that initial paper, even though the data is, and justly should be scrutinized. We've started thinking about blue carbon in a whole new way. So Ouyang and Lee, a few years later, put out a more extensive literature review to visit this idea of carbon accumulation rate. It's one of the most important parts of blue carbon. Again, that's on the y-axis, the same units, but not at log scale this time. And on the x-axis are 4 categories, and these are 4 different ways to measure carbon accumulation rate. M is marker horizon, feldspar marker horizon. The way you measure carbon, so-called carbon accumulation rate with a marker horizon is you put down a layer of feldspar. It's essentially like chalky clay. And you put it down on top of the marsh, you revisit it some amount of time later, and measure how much vertical accumulation is occurred on top of that spot. The vertical accumulation rate is multiplied by a carbon concentration of the material below it, and it yields an accumulation rate. You may be thinking that is kind of a strange way to measure carbon accumulation rate. It doesn't take into account any of the plant processes or the larger marsh area. And you're right. So there's some definite drawbacks to that. As a tally for the pro side of why to do it, it's cheap and easy. This is, and anyone can do this. There's not really any instrumentation required besides intelligence. Cesium-137, lead-210, and carbon-14 are radioisotopes. They all sort of have the same theory in that you can gauge the depth at which they're collected. Cesium-137 goes back to 1963. So you see one peak, get one depth, and you can inventory the amount of carbon above that depth, and you know the age. So dividing inventory by age, you get a carbon accumulation rate. Lead-210 works similarly, but resolves beyond 1963 to about the past 100 years. And carbon-14 has the longest half-life of all 3 of those, can resolve tens of thousands of years, and pretty much can age any marsh sediment during the Holocene. And so these categories are arranged left to right from the time that they resolve, from months, decades, centuries to thousands of years. And so the trend of data that Ouyang and Lee published, and they didn't ever really look at the data this way, but looking at it over this temporal scale, you can see the outliers that were also in the McLeod paper. These really high outliers would drive that very, very large error bar. And while 1,700 grams carbon per square meter per year might be true for that particular wetland at that particular time, those particular drivers, it's not a good representation of global salt marshes. And so using a mean as a central tendency for this type of data was kind of strange to me. Something like a median might represent the data a lot more. And you can kind of see this where the shorter amount of time that CAR is integrated over yields potentially higher values versus these longer century and millennial rates. Timescales yield lower rates. What's also interesting is that this oft-cited literature review is not exhaustive in any way. I think they used some keywords in Web of Science and just took those papers and didn't dig further. So looking at the distribution of data that make up their reported mean and median, these are highly biased towards marker horizons and cesium-137, which have higher rates because they incorporate shorter amounts of time. So I'm thinking about this problem. We don't, even with some of these literature reviews completed, we don't have a grasp of what CAR really is as a global mean, and how to project that over the global area to understand if salt marshes really draw down as much carbon permanently as we think we do. So just seeing that graph in photograph form, here's a core collected from one of our marshes with a Russian peat core. It's a great device that opens up right in the field, and you can see the core you collected and ensure that it's whole, and visually see some of the changes that happen. So this is the bottom of the core, and this is the Pleistocene sand that the whole marsh started colonizing thousands of years ago. And just roughly, if we were to measure the age of the marsh with these three markers, radiocarbon can measure all the way to the bottom of the core, basically. Lead-210, not as deep, but it's deeper than cesium-137, which is the shallowest measure. So one idea that we're about to visit is how important is it to integrate all of the organic matter that's accumulated in the core and over time, and how does the rate of accumulation change over time? Is it linear or is it not? So the main question that I'll be discussing today revolves around this simple equation, and the question is, does blue carbon mitigate climate change? To understand that, we need to understand the relationship between accumulation and decomposition. They're two sides of the same coin. How does carbon accumulate, and once it accumulates, how does it decompose? So we're going to start with left side of the equation and go into the accumulation here. In this next section of the talk, we're going to quantify long-term carbon storage in North Carolina marshes and compare it to previous rates, and then do our token global extrapolation and compare to some of these other studies that have done the same thing, but maybe been used a little bit less scrutiny with all the rates that they used. So again, I want to tip my hat to another scientist, and who apparently have a propensity to include pictures of old dead white men in my talks. But Alfred Redfield, who is of Redfield ratio fame, published a paper in Science, of course, which every good scientist publishes in, but it's probably because LNO, which he founded, hadn't been founded yet. He wrote a paper about the marshes in New England, and the first line of this paper is just fascinating to me. The existing peat of tidal marshes preserves a record of the conditions which existed when the peat was deposited. Just so elegant and perfectly put. And still, even to this day, this is why we take cores. This is just the same idea and same reason why we go and look at the marsh through time or downpour and try to piece together what has happened in the past. And so these cutaway illustrations, I think, show the complex dynamics of how the plant works to make its own platform of marsh. And so in this cutaway on the very left, this is a hypothetical, original plant. It's just got some small roots growing down into a mineral soil. But over years of time, those roots become thicker, and that original surface is now buried. And there's a new surface, which the plants are probably about the same height are coming out of. And through time, this peaty material, high organic material with deposited mineral soils has accumulated. And thus, if you go to a marsh that looks like this and core down, hypothetically with the right tools, you can figure out where this original surface is and what conditions existed at that time. So the other thing that separates wetlands from its terrestrial counterparts are some of the ecogeomorphic feedbacks that exist in the salt marshes. This is a fun little term that's been coined that talks about how the marshes or wetlands respond to external stimuli. And one stimuli that coastal marshes respond to that terrestrial forests or even freshwater marshes don't necessarily have to deal with is rising and falling of sea level. Sea level is always rising and falling. Currently, the rate of rise is accelerated, and one big question is how will salt marshes respond to this accelerated sea level rise? Will they keep pace or will they drown out? Well, they have these, I guess, within the ecosystem exists these ecogeomorphic feedbacks, and it works like this. So, for example, if sea level is rising, above ground plant growth will be stimulated, so the plant surface can be above sea level, which then enhances the mineral deposition from the flood tide. So plant stalks baffle the currents and sediment falls out of suspension, which then causes elevation gain, which then helps this marsh keep pace with sea level rise. So this is a positive feedback. With sufficient sediment supply, and given most rates of sea level, a marsh can keep pace. In concert with that is a below ground process where the root injection of organic matter causes organic matter addition and elevation gain through production of organic matter. So it literally lifts itself up, and you get elevation gain through just organic matter production. And so oftentimes these are both happening in concert. And so marshes can keep pace with sea level rise. Carbon accumulation rate then should be tied to sea level rise. So the faster that the marsh is growing vertically, the faster it's literally burying its own carbon. So that should be an aspect considered when you're measuring carbon accumulation. So let's do just that. We'll go down to the coast of North Carolina, Great North State. To orient you, if you don't know, IMS is probably about right there. And our study site is the New River here. And it's a choked lagoon that's lined with some marshes down here in the transitional zone, and also along the intercoastal waterway, which is this thin water strip here. So we occupied several of these marshes and took cores of the marsh. Classic ecologist and geologist tool. And so what we did with these cores is measure carbon accumulation. As I mentioned before, to do that, you quantify a carbon stock. We know the area of that core, divide stock by area and age of the bottom of that stock, and get carbon accumulation rate. So we can make the most out of our coring effort and do this multiple times through the core and plot carbon accumulation rate over the age. So this example plot has a reverse x-axis, so that 0 is origin on the far right, and the older the integration year, the further to the left of this plot. And so as through some of the aging tools I mentioned before, C14 and lead 210, we can get multiple ages of the same core over a series of cores and calculate CAR over a series of time to see how carbon accumulation rate changes. And so looking at real data, it follows this sort of exponential pattern that we, well, I guess we expected it. I'll say we expected it. That sounds smart. And that these oldest dates, the open circles, are relatively equal, but relatively low. We're a lot lower than the 2001 paper average of 244. But the more recent measurements towards the top of the core are much higher. Not quite 244, but in the triple digit. So what is the driver of these different carbon accumulation rates over time? As I suggested earlier, eco-geomorphic feedbacks should play an important role in this. And when plotting carbon accumulation rate against relative sea level rise for the North Carolina coast, these match up almost perfectly. And so this recent accelerated sea level rise is likely one of the main factors driving these higher rates, whereas these lower rates all occurred when relative sea level rise was much lower than it currently is. So just to get this point across, I've admittedly cherry-picked just a couple of values that get the point, drive the point home. And that if you integrate carbon accumulation rate over thousands of years, the rate ends up being relatively low. If you use a much younger integration time, the rate is higher. So I am not involved in this. I know at least two other independent efforts that are trying to do exhaustive literature reviews to sort of compare this over space and time and look at other environmental factors, West Coast versus East Coast versus Gulf Coast, rivers and estuaries and marshes, and look at some of the other drivers to try to get at to understand carbon accumulation rate better so that we can apply it to these global models. I don't have that at my disposal, but we can do some other exercises to try to globally extrapolate and get at maybe a better representation of carbon accumulation rate, at least better than what's been done before with our new knowledge. To answer our question, is blue carbon mitigating climate change? And so, again, our global rate is simply CAR multiplied by the area of salt marshes. We have a lot of information about what CAR is, but we know that the very low values are estimated over thousands of years and don't represent what coastal marshes are, the rate of sea level rise that they're experiencing right now. So it doesn't really make sense to use a carbon accumulation rate from thousands of years ago. If we're looking to estimate what current marshes can do. But at the same time, it doesn't make sense to use extremely high rates that were calculated using methods like feldspar marker horizons. They don't really measure carbon accumulation rate. So with some justification, we removed some of those outliers on both the high and the low side from this data set and formed a new distribution of what R is globally. We need to multiply this by area of salt marsh. This is astoundingly poorly understood. You know the area of continents and the forest, but marshes are really difficult to identify with aerial photography, satellite photography, because sometimes they're flooded, sometimes they're not. Where are the delineations between forest and marsh? And so the range is quite large. This upper estimation 400,000 kilometers was made in 1973 by Woodwell, who took the area of temperate, subtropical, and tropical coastlines and multiplied by some number. He said, oh, the average wetland is this wide. Multiplied by that number and said this is the upward maximum of what we think wetlands are. And we haven't been able to do better than that. On the low end, you often see 22,000 square kilometers as a representation of salt marsh. That number was presented by Chmura et al. In 2003, who clearly said in the paper, the United States, Canada, Europe, and the country South Africa have 22,000 square kilometers of salt marsh, although there's likely much more in the world. No one else has done a very good job quantifying anything past that. So in the McLeod paper and the seminal blue carbon papers, they use 22,000 to 400,000. I've taken the liberty and added some other salt marsh areas to that 22,000. So we have a higher low end, but I think it's beyond my own undertaking to do better than that Woodwell estimation. So now multiply this by this, but instead of just doing that once or using a mean average from this or mean average of this, you can set up a Monte Carlo type program to randomly sample from a normal distribution of CAR and a random distribution of salt marsh area, run that 10,000 times in R, and develop a probabilistic distribution of what global carbon burial might be. And have low ends, high ends, a median, and so now we have some certainty within the realm of uncertainty, which I've just described up here, that maybe we're dealing with about 50 teragrams of carbon per square meter. A teragram is somewhat arbitrary to me compared to what others have said, and we're all in the ballpark, even after scrutinizing these values and using new statistics. Folks have generally found this the same amount of carbon removal by salt marshes. Okay, so how does that compare to anthropogenic emissions? Well, it's completely dwarfed by that. Even as a best case, salt marshes are not even close to the 9,000 teragrams of carbon per square meter per year just from anthropogenic fossil fuel emissions. Okay, so you're probably saying salt marshes are just one kind of coastal ecosystem. What about all the others? Well, we can look at other estimates. We'll just take the high end and be very liberal. Even seagrasses, which I'm not sure can bury that much carbon. Macroalgae, which I'm not sure can bury that much carbon. Take this total of almost 300 teragrams per square meter per year. Again, dwarfed by the sheer amount of fossil fuel combustion. So I don't think coastal wetlands by themselves are going to undo what we're doing by burning fossil fuels. Do I think wetland conservation is a good thing? Yes, it's still very good. Wetlands perform several key roles, including sediment nutrient filtration, larval fish, nursery grounds, bird and other wildlife habitat. And that carbon burial, although small, is still a drop in the bucket. I mean that in the best of ways. And that this is a complex problem that doesn't, we shouldn't just be showing things that don't fix all of it as a panacea out the door. It's one way, one small way to help draw down CO2 from the atmosphere and geoengineer, so to speak, our problem. should it be touted as the reason to plant marshes and preserve marshes? No, because let's be frank, it's not doing this. But for a management perspective, if we manage, say, bird habitat, under that umbrella of bird habitat, you are innately managing carbon burial potential of a marsh. So it shouldn't be overlooked. But I would argue it shouldn't be carbon burial first. I think that's something that can fall under the umbrella of management. All right, so we've delved into some of the accumulation processes of the salt marsh. Let's look at the flip side of decomposition. So what happens during the breakdown of marsh? Some experiments have been done in the past using litter bags. This is a commonly cited one. They use Spartina, below ground biomass. And over about a year and a half, there's this beautiful exponential decline of root mass in the litter bag. So the litter bag doesn't really measure decomposition. It measures the decrease of POC in that litter bag. Let's see if that's become maybe DOC or DIC, maybe just really small POC and has gone through the pore size of the litter bag. But has it turned into CO2? I don't really know. The other thing that comes to mind as a former Arctic person is what was shown of this really old material once it melted and left its confines of permafrost and joined, I guess, these Arctic rivers in the East Siberian Sea. Well, the same thing is happening with marsh as it erodes or develops or experiences a big storm. This material that's locked away that we showed was thousands of years is now eroded into the surface and has a potential for breakdown. And this 20,000-year-old DOM from Yedema, 30% of it broke down in 2 weeks when exposed to surface conditions. So this potentially, if this trend holds true with marshes, as marshes are converted to, say, pastures or eroded away, we could lose a lot of that stored carbon that's thousands of years old right back into the atmosphere as CO2. And so I'll just quickly outline the decomposition pathways and why it's hard to get at. I mean, the litter bag studies aren't a bad idea, but the marsh, even though there are problems with marsh, draws down CO2, converts that to particulates, and upon erosion, the DOC can either stay in the marsh, it could be exported, it could just stay as DOC and never become CO2, but it would be lost from the litter bag. DOC can become DIC, which can be exported, but ultimately we want to know what happens, how much of that POC becomes CO2, how much of that is going into that feedback of climate change. And so our approach was experimental, and instead of doing this in situ, which has, there's a lot of problems in constraining all these fluxes, we did this in vitro and basically put all of this in a box or an incubation container and measured just the output of CO2 and didn't have to worry about these really complex interactions between the dissolved pools. And I like this picture a lot. This is one of our study sites. And if you just step forward into the picture, you can see why this is an important idea, because the marsh here is eroding in these large meter by meter by meter chunks. And it's just it's a high energy, like episodic event where this material that was buried away in a toxic, dark environment, preserved is now exposed to sunlight, to different temperature regimes, and most importantly, oxygen. And will this material become CO2? Our current understanding is largely rests in two papers, and this Howard et al. Paper basically copied the same table out of a paper by Pendleton et al. And basically did this for mangroves, marshes, and seagrasses. We'll just focus on marshes. They took this extent, here's that 2.2 that I was complaining about. You can do better than that. And calculated how much is sequestered, how much of that is the current stock, how much of that stock is converted. So 1 to 2% is fine. But then how much of that 1 to 2% of the stock becomes CO2? But it's never really been measured. And both of these papers just use this range of somewhere between 25 to 100% conversion. That's a huge range. And 100% means that all of the carbon that's eroded becomes CO2, all of it. That just sounds outrageously high, especially since very few real measurements exist. So let's actually measure this and see if we can constrain these values a little bit more. This is sort of just a schematic of our drawing. I said, let's take all those really complex interactions with the dissolve phases, put them in a box. Here's our incubation chamber. Here's our sediment. We'll measure CO2 production over time. We also measure methane. This is an oxygen environment. We didn't have any methane production. And we'll measure that over time with a greenhouse gas analyzer. We did this from 2 different depths of marsh at 2 different temperatures, 20 and 30 degrees. And we got these beautiful linear rates over 160 days. So about half a year, we ran this experiment. And what we thought the quality of the material would really drive this. So the more labile, the younger material at the surface would decompose faster than the less labile, deeper material. But what we found was that this reaction of marsh material decomposition is temperature sensitive, and that the warm 30-degree treatment of both the shallow and the deep sediment decompose faster than their analogs at the colder temperature. And this is really interesting, and also makes analysis a lot easier, because this breakdown is happening through mostly bacterial extracellular enzyme digestion. And this is the microbes are the ones ruling this process. And so now that we have these linear rates at 2 different temperatures, we can model this using kinetics of enzyme breakdown. And here we go. This guy again has this really fantastic equation that explains just that. Just to remind you of your biochemistry, this Arrhenius equation is basically y equals mx plus b. Just a little bit more complicated, but it basically says if you know the rate at 2 different temperatures, you can calculate Q10. You can also calculate the activation energy, and we can do that from our experiment. And then if you know the rate of whatever process you want to measure at 1 temperature, you can calculate it at 2nd temperature. And so this is helpful because we know the marsh isn't always 20 degrees or 30 degrees, which is what our experiment shows. The marsh has a very wide range of temperatures, which luckily through some monitoring work, we have temperature data from every 6 minutes. So this is a histogram of that data over 1 year. And we're, North Carolina is temperate, so we got some hot days, some cold days. Like I said, we know the rate at 20 degrees and 30 degrees, but using Arrhenius, we can calculate the rate of decomposition at any of these temperatures. And let's integrate over an entire year of temperature, what an entire year of decomposition is. And I'll argue that 1 year is probably a good time to measure this process over. Everything's eventual, yeah. So we left this out for hundreds of years. Yeah, maybe we would get the 100% decomposition. But this is a dynamic habitat. It's flooded daily. There's storms. So after a year, I think this eroded material would either be reburied in the creek, reburied on the marsh, or exported to a shelf where different sort of burial and decomposition dynamics would take place. So over a year, our new decomposition rates are so millimole per mole. It's kind of like a percentage. That's 23 and 17% loss over 1 year. And so that lets us update these previous estimations of marsh decomposition. We'll update our minimum marsh extent, 2.2. We'll leave this, that's fine. 25 to 100. We'll use 17 to 23. And so our potential emissions from marsh conversion, it's constrained a lot from previous estimates. Our low side is higher, but that's because we're not estimating only 2.2 megahectares of marsh. But our high side is almost half, because 100%, that's just ridiculous. It seems unreasonable. And now we have experimental data to back that up. So, in conclusion, thinking about the controls of storage, and this back and forth between accumulation and decomposition, I think the take homes here is to really think about the methods which you use to measure something, make sure it's really measuring that thing. And even in papers might use the same units or say the same words, but not all methods are synonymous. The amount of carbon sequestered by coastal habitats is fractional to anthropogenic activities. But as an upside, the temperature sensitive marsh decomposition reactions are fairly slow, a lot slower than the Siberian Yedema, for example. And so even as marsh erodes or falls apart, we're not seeing 100% decomposition. And so just sort of some final thoughts on this as a whole. Daniel Kahneman is a behavioral economist, and as I think we don't spend enough time thinking about other disciplines, but I really liked how he explained this idea. He says, there's a real social problem that if you realistically present to people what can be achieved in solving a problem, they'll find that completely uninteresting. You have to overpromise in order to get anything done. And that's, not only is that sort of what blue carbon is, that's sort of what life is. I mean, if you don't promise double and say you can do it for half the price, no one's ever going to listen to you. You're going to get your NSF funding. Your spouse will always be mad at you. That's sort of human nature, and that we constantly overpromise and then set that goal and try to get it. But even in science, which is oftentimes just put up on a pedestal, it's not always what it initially says it can be. And that's because it's a constantly evolving process. And I think to counter that cynical viewpoint, sort of put out there, this Edwin Hubble quote is really good. And he said, the scientist explores the world of phenomena by successive approximations. We know that our data are not precise and that our theories must always be tested. It's quite natural that we tend to develop healthy skepticism, suspended judgment, and disciplined evaluation. And so, to me, this is the world of the scientist, is over-promising, thinking creatively about new ideas, and trying to get there, but also scrutinizing everything, never just accepting what people tell us, and that's how we continually evolve that process. And the last part, which is the real take-home of this talk, I think, wetland conservation is a win-win. No reason not to do it. Carbon sequestered is not enough to mitigate climate change, but it is a small fraction that can. So that I acknowledge a whole slew of people who've helped either in the field, in writing and in thought and development of these ideas, with analysis and funding resources. And with that, I'll take questions.
I thought that visualization of the different geochronological methods from OEA and HAL was really cool. I never really thought of it that way. I knew like cesium dominated, but not violet. Have you also thought about looking at how they measured carbon in the same way, whether they did like an approximation or whether they directly measured carbon?
I haven't, but yeah, it would be doable. This was sort of a low-hanging fruit because in their table they have which method it was, and I think to do
They're more vague in that paper.
You'd have to go back to each individual study and sort of recreate the table, but yeah, it is an interesting thought.
You hit on some of the complexities of getting the carbon accumulation rates. The sedimentation rates depend on your methodology, which may reflect real changes in sedimentation rate over time, or could be logically related. And that some of the carbon that's accumulated may remineralize, over, especially because what's relevant in terms of sequestration from the atmosphere has to be at least several hundred years. If it's a year or 5 years, it's really not a benefit in terms of climate. But if you can get up to 1,000 years, now we're talking about climate benefit. And certainly some of that is going to remineralize on a 1,000-year timescale. But another complexity that I really haven't heard talked about, and I don't know if it's significant or not, is that there's mineral material in the sediment, and a lot of and these salt marshes are natural sediment traps, and so part of the accumulation is basically clay minerals, whatever, with associated organics and things that may be quite refractory, and so part of that organic matter that's being sequestered actually may be refractory material, in a sense double count. What you're doing is you're accumulating stuff that really doesn't matter where it goes. It's going to just basically, it's carbon-14, it's really old, and it's just for whatever mechanism is refractory. And so in order to monetize this thing, you have to get all three of these things right. You really need to know how much is accumulating, what fraction of it is going to decompose over a 100-year time scale, and what fraction that would be buried anyways. And so it's almost like going to the store and they hand you a bag of cherries for $5. And and it may have free cherries, it may have like a lot of cherries, and you don't really know. But sort of the added sort of interesting thing about it is people who are buying carbon for carbon trading, they don't really care if it's right or not. They just want a number that they could say offset all of our oil use. So anyways, those are just, I really want to hear your thoughts on whether you think there's some portion of that carbon buried may actually have arrived already refractory.
Yeah, that's a really good point, and we end up pulling our hair out over that. For example, what if it's terrestrial, organic, woody, lignin-rich material that just got deposited on the marsh, and it's buried in before we count that. And so it comes into play when sort of doing a full ecosystem carbon budget, fluxes and influxes and defluxes. That's one reason why I sort of highlighted seagrasses as maybe not a place where carbon accumulates as high as they think, because the seagrass carbon isn't the refractory amount of carbon that is deposited, because oftentimes it's not seagrass carbon. And so I think through some stable isotope work that I've done, and a little bit of lignin tracers, a lot of the material, at least in these marshes, is marsh derived. I can only say that I wouldn't say that all of it is. That's, and some amount wouldn't be. The other interesting aspect of the carbon decomposition world is there are these ligand bound materials, or essentially like a macromolecule that has carbon in it, but it's in a shape that enzymes can't attack it. And so it might be quote unquote like maybe it's an amino acid or something that's stuck in, but because it can't ever be the enzyme can't ever reach it, it's forever bound in this sediment. And so if that sort of material was arriving, then yeah, we would be double counting it. If it was leaving the marsh, then it would supposedly still be bound, but we had some sort of tracer to know that was marsh carbon, and it ends up on the continental shelf, then it would be a lot easier to account for. But for the most part, I think in the marsh, the majority of the material is marsh derived, and a majority of the mineral sediment is inorganic. At least for our marshes. But yes, you hit on one of the most critically hard parts of defining carbon for the monetization aspect. So who gets the credit, and we make sure to not double count.
So my question is kind of related. At the same time as the blue carbon became a thing in marshes, marsh outwelling of dissolved inorganic carbon was being developed as an idea in estuaries, and especially in the South Atlantic bight, really like very productive marshes. The outwelling of DIC shifts the carbon equilibrium towards CO2 and supports really large CO2 emissions from those estuaries in particular. But despite that, we don't have a really good understanding of the interface between marshes and estuaries. That flux is not really well understood. So even through our DSRP carbon budget, we weren't. It may be implicit in there, but we really don't know how it works. Does your incubation work or any other work help to inform that flux? Or if not, what are the next steps in addressing that?
Yeah, I think it helps. It definitely helps in some respect. So it's somewhat straightforward exercise to take aerial imagery and georectify it and measure area lost to erosion over time or gain. But using but now that we have empirical values to assign to that loss, say, okay, we're losing 25% CO2, so 75% is going. So I think it helps constrain the big unknown. 100% all staying, is it all going? And yeah, the lateral transport, especially between good zones, is another tricky thing. And yeah, I really thought much about it until the DSRP project. Watching everyone pull their hair out and try to make methods talk to each other over the same time scales. It is a huge task, but yeah, I need to get those numbers out quick. I think it can be applied a lot of ways.
So, talking about how long carbon is sequestered,
Mhm.
in these reservoirs. And one approach is residence time CO2 in the atmosphere, well, that's hundreds of thousands of years. Don't coastal managers have a time scale they talk about in terms of speaking of how valuable reconstructed marshes or built marshes are in terms that they have to sequester a certain amount of time that's ridiculously low?
I don't know.
I think it's like 20 years. So
20? Yeah, good. I should ask Caroline or Jenny. They would know.
okay, yeah.
For sure.
So there's a certain disconnect between who are actually assigning values to it and those who are thinking about it in terms of designing. It problem in some of these more subtle kind of things.
Yeah. One thing that we talked about almost exhaustively is 100 years. It's just such a nice round number. Oh, slap 100 years on it. That's easier to quantify. It lines up with lit 210 chronology. And as far as climate mitigation, 100 years isn't mitigating much. Even if the molecule is sequestered for that long. Yeah, so it is interesting.
The questions? Questions in post? All right, with that, let's thank Nathan again. And there
Just straight back. I remember, what was it? Was it your notebook or before I walked in with it? It said like, this.
OMG, that's what I said.
Oh, yeah.